Okay, next is that your computation of line flows and line losses, right. So, here also you will think that way, right. This we have already studied that transmission line and pi representation. You have seen, no, that that when you are making like this, when you are making like this, your what you call this this is sending end, right. I am making in my way, right. Say this is your sending end line and this is your receiving end line, right. And both this side you have your charging admittance, right, and this side also you have charging admittance. In that case it was y by 2 and y by 2. If this is your sending end and this is your receiving end, right. So, this is the line current and some current, say I c is going to this, and this is your the way we represent the tie line, no. This is your sending end and this is your line impedance, that is Z, and this side is your you have that y by 2 and this side is your y by 2, right. This is y by this is y by 2, this is y by 2, right, y by 2, and this is your plus minus, this side is V s and this side is your V r, right, and this is your sending end current, and if this current is your I c, say for example, and this current is your line current. So, I s is at this point, if you apply KCL, I s is equal to I L plus I c, no. So, if you know this, then look at this. You should not be just looking at this, there is nothing to be this thing. So, suppose you consider bus I and bus k, this dash line are shown, this thing when line this bus I may be connected to some other buses, bus k also connected to some other buses, right. So, instead of line impedance we are making it y I k, that is line admittance small y, right, and instead of sending end or receiving end those things, this is we are taking current I I k and this is I I k 0 going to the shunt admittance, right, shunt admittance, right, and this side and this line current here it is I I k dash, right, and it is y I k and it is I I k 0. Similarly, and this power actually going to this we are making it like S I k, I to k, S I k. Similarly, bus k actually we are making power as S k I, k to I, and current here it is I I k, here it is I k I, k to I, right, and here the charging admittance is there, it is y I k 0, it is y k I 0, right, it is I k I 0, here it is I k I 0, here it is I k 0, right, capital I suffix I k superscript 0, right. So, and this is bus I bus k, this is pi representation of a line between two, this is actually a pi representation you have seen already, but this one we are representing by instead of impedance that admittance y I k of the line, and this side we are showing I I k, this side we are showing I k I, right, that is the thing. And in this case you have to write few equations. So, it very easy actually, right. So, if you make it like this and this is your figure 6. So, from figure 6 actually we can write I I k dash is equal to V I minus V k y I k. So, this current line current is actually I k I or I k dash, actually this y k instead of drawing at the, instead of making it from the bus bar, right, then it does not look good, right, but so that is why I made it here actually this I k dash, it is actually it is V I, this I have made it here and here, right, but actually it is all these things lumped together, I mean make it at the bus I only, but then I cannot show I k or S I k. So, that is why I made it like this. So, your I k dash, that is this current in the line y I k actually V I minus V k, that is V I is the voltage of bus I and V k is the voltage of bus k. So, that is why I k dash is equal to V I minus V k y I k, but I k, this I k apply at this node, just now I told that Kirchhoff's first law I k is equal to I k dash plus I k 0, right. That is why I I k is equal to I I k dash plus capital I, right, capital I suffix I k dash plus capital I k superscript 0. This is equation 23, and this I I k dash is equal to V I V k minus small y I k, and I I k 0, this one, this voltage is V I. So, it is actually y I k 0 into V I, right, it is at ground potential. But if I put it here and here everything, it will become very clumsy, very difficult to explain then. That is why for clarity this way this has been drawn, right. So, I k 0 is equal to that. Now, from equation 23, 24 and 25, nothing is I k dash you substitute here, I k you put 0, put it here. So, you will get I k is equal to V I minus V k small y I k plus V I y I k 0. This is equation 26. This is required because computation of line flows and line losses, right. Now, power fed into the line from bus I, S I k is equal to P I k plus J I k. This is S I k, power fed into the bus. So, this is shown like this, right. So, power fed into the bus is your S I k is equal to P I k plus J Q I k. This is equation 27. Now, we know that P I k plus J Q I k is equal to V I k conjugate, right. Therefore, this equation 28 and this 28 and 26. So, I k is equal to this equation is I k, right. So, you put it here. So, the I k, this equation of I k you substitute here, that is why you substitute, that is why for using equation 28 and 26 you will get P I k plus J Q I k is equal to V I in bracket, this is your I k, V I minus V k small y I k plus V I small y I k 0. So, superscript this whole conjugate, that means P I k plus J Q I k is equal to V I whole conjugate you take. So, V I conjugate minus V k conjugate, the small y I k conjugate plus your V I, your this thing, this multiply this by the V I, right, this is also multiplied by V I, then V I into this V I conjugate, V I into V I conjugate, then y I k 0 is conjugate, right. So, that means your this thing actually directly also you should have made it P I k minus J Q I k V I conjugate I k, directly you should have also made it. After that again I have taken P I k minus J Q I k. So, in that case P I k minus J Q I k if you take, it will be basically V I conjugate V I minus V k y I k plus V I conjugate V I y I k 0. You take the conjugate of this equation, or this equation you can take P I k minus J Q I k is equal to V I k V I conjugate I k, this I k directly you can substitute, same thing whatever you will get here, right. So, you will get this one, that means now P I k minus J Q I k multiply this V I conjugate V I is magnitude V I square y I k minus V I conjugate V k small y I k plus V I conjugate V I means magnitude V I square y I k 0. This is equation 29. Similarly, power fed into the line from bus k, that means this equation, that power fed from the line bus k, that is S k I also there, right. So, you need not derive it. What you can do is in this expression, just in this expression equation 29 interchange k and I. So, because it is I k k I, so just interchange. So, I have just interchange, you will get the same expression, just look how it is, that it will be, it was I k, it is k I, it is I k, it was minus j q k I is equal to, instead of I it is V k square, that y I k and y k I same. So, small y I k, right, minus it is V I conjugate, it is V k conjugate, it is V k, it will be V I, and again small y I k, because y I k is same, plus it is V I square magnitude, it will be V k square, it is y I k 0, it will be y k I 0. So, similarly power fed into the line from bus k, just interchange k and I in equation 29, right. Now, capital Y I k is equal to minus small y I k, this we have seen earlier also, we have taken this, that means small y I k is equal to minus capital Y I k, right. From here you can write like this. So, in these two equations, 29 and 30, you replace small y I k by minus capital Y I k. So, that is why writing from equation 29 and 31, right. If you do so, you will get P I k minus J Q I k, first see is minus magnitude V I square capital Y I k plus V I conjugate V k capital Y I k, right, plus V I square magnitude small y I k 0, because this charging admittance, right. Now, same as before, you write capital Y I k is equal to magnitude y I k angle theta I k, then V I is equal to magnitude V I angle delta I, V I conjugate is equal to magnitude V I minus angle delta I, and it is a charging admittance. So, y I k 0 is equal to j magnitude y I k 0, it is charging admittance. So, kappa that we have seen earlier also, it will be j magnitude y I k 0. All these things you substitute in this equation, then we will separate real and imaginary part, right. That means, if you substitute and make it like this, it will become p I k minus j q I k, real part will become minus magnitude v I square y I k magnitude cos theta I k plus magnitude v I magnitude v k magnitude y I k cosine theta I k minus delta I plus delta k. This is the real part, minus j in bracket magnitude v I square magnitude y I k sin theta I k minus magnitude v I magnitude v k magnitude y I k sin theta I k minus delta I plus delta k minus magnitude v I square y I k 0. That means, this equation you substitute all in this equation and you just make real part imaginary part, right, separately, right. So, that means, this is the equation. Now, you separate real and imaginary part. If you do so, this is your, this real part is your p I k and imaginary part will be your q I k. So, p I k will be this one, right, whatever it comes, equation 34 it is, and q I k will be the imaginary part is this one. That means, this is the real power flow p I k and this is the real reactive power flow from I to k, right. Now, before going to this thing, suppose you have a bus bar, suppose you have a bus bar, this is say ith bus and this is kth bus, right. Suppose at this point, suppose if line has impedance z is equal to your r plus jx, line has impedance, right. So, at this point, if you suppose power flowing is this direction, right. So, and this side you take this direction. So, at this point you measure the power, right. Suppose at this point if you measure the power, for example, suppose you have a watt meter here, suppose you are measuring, right, use power you measuring using your what you call for transmission line. So, directly you cannot measure, you need CT, you need CT, PTs, everything. Suppose you measuring power here, right, you are measuring power here, suppose you got this power is 100 megawatt, right, but in between when you will measure at this point, say flowing in this direction, right, in this point if you measure, because I square all loss is there. So, here your power is not 100 megawatt, right, it is not 100 megawatt, write clear, let me write clearly 100 megawatt, it will be suppose flowing in this direction, power flowing in this direction. So, here for example, here in this direction is here you measuring at here you are measuring, right, say here it is 99 megawatt, in that means in this direction it will be minus 99 megawatt. That means, your I to k, that means power p to I k is equal to 100 megawatt, you are measuring here, and this side when you take q k I, that is your minus 99 megawatt, because direction is changed, this is the direction, but here it is 99, but direction is changed. So, minus 99, that means power loss of the line I k, P loss I k is equal to P I k plus your what you sorry, this is P I k, this is P k I and this is your this is your P k I. So, P I k is 100 megawatt and this is your 99 megawatt, that is 1 megawatt power loss, right. That means, here you are measuring 100 megawatt, here you are measuring 99 megawatt, that but direction is this way, when you take this direction it will be minus 99, that is your P I k and this P k I is minus 99, right. Therefore, P loss, let me write clearly, P loss I k is equal to P I k plus P k I. So, P I k 100, P k I minus 90, so it is 1 megawatt. So, that is why here P I k expression we have got, Q I k expression we have got. Now, K to I interchange in these two equation K to I, that replace interchange, just make instead of I k and K to I, right, replace I by k and k by I in these two equation, then what you will get, this P k I expression will be your this one. I mean equation 34 and 35 you interchange I and k. then you will get the expression of pki. This is the expression of pki and this is the expression of qki, that is your, this is equation 36, this is 37. These are power flows from k to I and reactive power, the real power flows, reactive power flows from k to I, right. Now, the real power loss in the line I k is the sum of the real power flows determined from equation 34 and 36, right. I told you just now that I to k it will be p I k plus p k I, that how things are happening, right. That means, P loss I k will be your p I k plus p k I, right. Now, this p I k and p k I, these two expressions are known to you. So, what you will do, these two expressions you p I k is also known and p k I is also known, the equation 34 and 36. Now, do you add these two? If you add these two, the P loss I k expression will become minus magnitude V I square y I magnitude y k cos theta I k. Then I am not telling again and again magnitude V I V k y I k cos theta I k minus delta I plus delta k minus V k square y I k cos theta I k plus V I V k y I k cos theta I k minus delta k plus delta I. This equation is equal to, it can be written as minus in bracket the magnitude, of course, voltage magnitude V I square plus V k square bracket close, then y I k again magnitude of admittance line y I k, that is your capital Y I k into cos theta I k plus magnitude V I V k y I k in bracket. This equation you can write that cos theta I k minus delta I minus delta k, right. So, this one cos theta I k minus take common delta I minus delta k, and this one cos theta I k, it is plus delta I minus delta k, this way it is written. After that, what you do, this one you expand it as a cos A cos B plus sin A sin B, and this one cos A cos B minus sin A sin B, and simplify. If you do so, you will get minus magnitude V I square plus magnitude V k square bracket close into y I k cos theta I k, and plus if you when you will expand it, you will find that your theta cos theta term will be cancelled, right. These things your what you call this your that sin thing will be cancelled, because this cos A cos B plus sin A sin B, this way you make it, and cos A cos B minus sin A sin B, you will find sin thing will be cancelled. So, it will become, so basically 2, because of it is 2 magnitude V I V k magnitude y k cosine theta I k cosine delta I minus delta k, this expression you will get. That means this equation you can write is equal to P loss I k is equal to 2 magnitude V I V k cos theta delta I minus delta k minus magnitude V I square minus magnitude V k square bracket close magnitude y I k cos theta I k, equation 30. This simple form of this equation you will get, right, after simplifying all this. So, these are straightforward, you can do of your own also, everything I have told, right. Now, further this one further it can be simplified, right, this equation further can be simplified. You assume let capital Y I k is equal to G I k plus J B I k, right. So, this way you define conductance susceptance, right, G I k, this way you take the G I k plus J B I k, and then you can, if it is like this, then G I k will be Y I k cos theta I k and B I k will be Y I k sin theta I k. If you define like this, right, that means this your what you call this Y I k cos theta I k, we can make it G I k. Therefore, here in this expression Y I k magnitude Y I k cos theta I k will be replaced by G I k, that is equation 38. So, if you do so, then P loss I k will become this, putting first G I k in bracket multiplied by 2 V I magnitude V k cosine delta I minus delta k minus magnitude V I square minus magnitude V k square. This is equation 39. This is the loss formula for your what you call line I and k. So, in terms of bus voltage magnitude and its bus voltage angle also, right. So, this is the and that your what you call G I k, that capital G I k, the conductance, right. So, this is the formula for the line loss. Of course, standard formula you know, that is simple thing is I square R, right, but this is required for many places, right. Later if time permits, at the end I will try to tell you, right. Similarly, if you make Q loss I k, similarly Q I k plus Q k I, Q I k expression is known to you, Q k I also known to you, add these two and simplify. Only in this case the charging admittance term will be there, because that is reactive component, right. So, in this case it will become Q loss I k will be B I k, right. It will be magnitude V I square plus magnitude V k square minus 2 magnitude V I V k cosine delta I minus delta k minus then in bracket magnitude V I square y I k 0 magnitude again plus V k square y k I 0, right. This is equation 40. That means, this is the expression of your Q loss. So, from this what we have seen, we have found that your loss formula use for the line I and k at the same this thing what you call your and previously we saw power injection P I Q I, right. So, this is the loss formula for the this is your reactive power loss formula. In that case charging admittance will come. If it is not there, then it is 0, right. If it is not there, then this term will vanish, but for all transmission line it will be there. Another thing is that for the further simplification I am just telling it that generally if you assume that delta I minus delta k, the difference is very small. If you assume it is very small, then cosine delta I minus delta k will be 1. So, in that case it will be 2 magnitude V I upon V k minus V I magnitude V I square. I mean it is something like this. If this P loss I k is equal to G I k 2 V I 2 V k, right, then cosine delta I minus delta k minus V I square minus V k square. Now, if you take delta I minus delta k approximately 0, then cosine delta I minus delta k it is 1, right. So, if it is so, that means this P loss I k it can be written as G I k, that 2 V I V k then minus V I square minus V k square. This one you can write minus G I k actually magnitude V I, right, minus magnitude V k whole square. This is minus minus, so take minus common. So, magnitude V I minus magnitude V k whole square, right. Then as you have taken capital Y I k is equal to your minus small y I k, basically the G I k will become negative, right. When you solve numericals, G I k will become negative. That means this term actually will become positive, because right. So, this thing, so your this V I minus V k whole square, this way you can take, right, and this is that simplest version. Of course, reality it is not true, right. For transmission system delta I minus delta k, similarly for Q loss I k also, that first 3 terms you can made it like this, right. Similarly, here also if you assume this is delta I minus delta cosine delta I minus delta k approximately 1, it will be B I k then bracket V I minus V k whole square minus this term, right. This will be there. So, this is your what you call that your regarding Gauss-Seidel loss formula for this thing, and P I k, Q I k, all these things are known, right. Now, algorithm for Gauss-Seidel method, first is the step 1. Instead of flow chart, I prefer that algorithm, right. Initially, with the load profile known at each bus, that means at each bus PLI, this is step 1, right, step 1 initial computation. So, that is PLI and QLI are known, right. You have to allocate PGI and QGI to all generating units, right. If it is for PQ bus, if it is a PV bus, then PG will be known, QG will be unknown, right. So, while active and reactive generations are not allocated to the slack bus voltage and its angles known, right, and these are permitted to this thing or vary during iterative process, that is active and reactive generation at the slack bus, right, and this is must as voltage magnitude and phase angles are specified at slack bus, this is known. With this data, net bus injected power Pi plus Jqi at all buses are known after the other than the slack bus. If it, I mean if all buses are PQ buses, right. So, this is the first step, that all the data you have to prepare. Second step is you form the Y bus matrix, that is line parameters are given. So, second step is that you have to form the Y bus matrix, right. Then third step is the iterative computation of bus voltage, right. To start the iterative process, you have go for a flat voltage start. Suppose slack bus voltage is given, if it is 1 plus J0, then initial values of all bus voltages except PV bus, because that voltage magnitude is specified, you consider that voltage, initial voltage of all, if you assume all the PQ buses, all the initial your what you call voltages should be equal to the slack bus voltage, flat voltage start, right. So, if the slack bus voltage is equal to 1 plus J0, then all other initial values of all other bus voltages PQ buses, right, it should be 1 plus J0, right, but slack bus voltage is known, right. So, this is the third step. Now, fourth step will be third step, and here also in the third step itself, right. So, in this, and then it should be noted that n minus 1 voltage equation are to be solved. That equation all the equations, that if bus 1 is a slack bus, then V 2, V 3, V 4, all the equations you have to make it, that we have seen, right. All these things you have n minus 1 number of complex voltage equation V 2, V 3 up to V n. First you have to make it, then you have to solve it, right, because bus 1 is a slack bus. After this, you have to see that your what is the voltage you have got, then you have to check the convergence. So, this already we have discussed, that take this convergence criteria, delta V is equal to max of absolute VIP plus 1 minus VIP, P is the iteration count, is less than epsilon. So, check epsilon you have to specify in the your data file. So, epsilon you make 10 to the power minus 4 or minus 5, right, and see and check the this thing whether solution has converge or not, this you have to check. If it is not, iteration will start. We will take an example and we will show up to 2 iterations, how 2 or 3 iterations how Gauss serial is doing, right. After this, computation of slack bus power. Slack bus power can be computed using equation 15 and 16. Let me search equation 15 or 16, right, just hold on. If I get it, I will show you, because papers are mixed up, right, just hold on. That is equation 15 and 16, just hold on. Just hold on, I will show you 15 and 16, if I get it quickly, or otherwise I will tell you. This is 15, this is equation 15 and this is 16. In this equation, you put I is equal to 1, because slack bus is 1. So, k is equal to 1 to n V 1, then you make V k y 1 k cos theta 1 k minus delta 1 plus delta k. Same equation we are writing here, k is equal to 1 to n magnitude V 1 V k y 1 k cos theta 1 k minus delta 1 plus delta k. This is equation 41 we are marking, right. Similarly, for q 1 is equal to minus, here you put I is equal to 1 minus k is equal to 1 to n, this is magnitude V 1 V k magnitude y capital Y 1 k sin theta 1 k minus delta 1 plus delta k. This equation we are writing minus q 1 is equal to minus k is equal to 1 to n, the same thing we are writing, putting I is equal to 1 in this equation 16, and here it is equation 15, right. Once you do this slack bus power computation, you have to make it using this equation, when I is equal to 1 in equation 15 and 16 you put I is equal to 1, right. Once you have done it, right, then this computation of line flows, right. So, in this case, this is the last step, right. So, line flows equation, power flows, all the you have using equation 34 and 35, right. So, PIK, QIK, all these equations those your what you call, if solution has converged, right, then equation 34 and 35 use, all you have derived now PIK and your QIK. So, that way you can find out what is the power flows. those expression and put those values. So, this is equation 34 and 35, and real and reactive power loss for the line can be computed using equation 39 and 40, that also we have shown, no, P loss I k and Q loss I k, equation 39 and 40. So, that way also you can solve it, right. So, the example we will take later, right, example we will take later, but before that I am giving you one interesting problem at the beginning of this lecture, when you take that your structure of the power system and few other aspects. At the end I gave you something. For example, this one you will do of your own. For example, this is sending end voltage and this is your receiving end. This is sending end, this side voltage is say P V s and its angle is delta s, right. This your this thing, and this side is V r and angle is delta r, right. And this line impedance, say I am putting a small r j, this is the total impedance of the line, this resistance, this reactance, right. And this side load is there at the receiving end. This is P r plus j q r, right. Now, this current actually flowing from sending end to this thing is, say this is the current I, right. Charging admittance you do not consider, right. Then what will be the relationship between sending end and receiving end voltage? This is given, right, and this expression is given. Now, question is that I have to find out that receiving end voltage in terms of sending end voltage, R value, X value, P r and Q r, this you have to find out. And another objective is, if I want to maintain this voltage magnitude, that is the sending end voltage magnitude is equal to the receiving end voltage magnitude, then how much capacitive compensation I need here, right. This is the thing. So, before that, right, this is the second case. First case is I have to obtain a relationship between V r, V s and P r, that whatever we have seen, if I recall correctly, then magnitude V s is equal to magnitude V r plus magnitude I in bracket, that is r cosine delta r plus x sine delta r for a short line, we have seen that, right. But in this case, if we want to make, then how we will do it? So, I am giving you this thing, suppose this is, first do not say that this is your sending end and this is your receiving end. So, this is your V s angle delta s, this is your V r angle delta r, right, and this one is your load P r plus j q r, this is the current I, this is an exercise for you, nothing to relate with the load flow studies, this is an exercise for you. Example Gauss serial we will take next thing, right. So, what you can do is that one equation I equal to, right, V s angle delta s minus V r angle delta r divided by r plus j x. This is one equation, equation 1. Another equation is P r minus j q r is equal to V r conjugate, that is I r. V r conjugate means it is actually this is magnitude V s, right, this is magnitude actually, right. So, previous diagram also it will be magnitude, right. So, it is V r conjugate, that is your V r angle your minus delta r, because it is conjugate, into this I this is your it is I am taking I, so I, right, you can take I is equal to I r also, no problem I. So, into your V s angle delta s minus V r angle delta r divided by r plus j x, right. This way this equation will come, P r minus j q r. Now, question is, in this equation you will separate real part and imaginary part. After that you will try to eliminate these deltas, that is delta r and delta s, right. And I am giving you one expression, that is an exercise, that when you will do this you will find out, right. So, separate real and imaginary part, and we have to you have to eliminate delta, right. If you do so, that equation will be that receiving end voltage, this expression will become V r to the power 4 plus in bracket 2 P r, right, into r plus 2 your q r into x minus that I can put like this, minus your this voltage sending end voltage magnitude square bracket close into V r square, right, plus 2 no, not this, plus your P r square plus q r square into r square plus x square is equal to 0, right. So, this equation whatever I have showed, this is an exercise for you, nothing to relate with load flow. Gauss Seidel will come next thing, then exercise for you that these two equations will write, and using this expression will make it by eliminating delta, the relationship between your what you call receiving end voltage and sending end voltage. This is the relationship. I hope this equation from my memory I have written, I think I have written correctly, right. So, this one you will make it, and solution now we will in the next lecture we will see the solution of this how to make the numericals using this thing for load flow studies using Gauss Seidel method. So, thank you.